Okay, so we all know this industry has made a recent kind of hard right turn from building ever faster CPUs to ever wider, more parallel CPUs. And this has created kind of a new grand software challenge that you've seen ample evidence of in this OSDI, that parallelism makes programming a lot harder in a number of ways. And in particular, it introduces non-determinism and data races, which produce Heisenbugs. And we don't like it. In fact, races are everywhere. They're not. They're obviously they appear at many levels of abstraction, as you've kind of already seen in the last talk. They're at the memory access level, where two writes to the same variable can race to produce non-deterministic results in the variable. A read can race with a write to read a non-deterministic version of some variable. You have all the same races when you're accessing shared file systems, for example, not only when you're doing parallel reads or writes to the same file, but also just in file manipulation operations like an open racing with the rename. And this can create time of check to time of use vulnerabilities and lots of security vulnerabilities as well as programming bugs. We've got synchronization level races. These are sometimes called high-level data races, where you might have a variable all of whose uses are perfectly well synchronized. I have locks around all uses of this variable x, but the semantics, the way I'm using that variable, since the locks can be acquired in arbitrary order, you still have more of this kind of internal non-determinism that Tom was describing because of the differences in lock order. And finally, even system APIs introduce non-determinism in lots of kind of subtle way. For example, if you've got two threads mallocing a block of memory concurrently, they can race to get a particular block of memory, and the pointers they get back will be non-deterministically different. And the same with, say, concurrent file opens. And this is kind of non-determinism that comes out of the memory allocation in file tables. So, of course, we can live with races, right? First of all, we can just not write buggy programs. Failing that, we have a lot of good and very useful tools to help us live with non-determinism, live with races. We have log and replay tools, race detectors, and deterministic schedulers, such as we just saw. These all help in different ways to manage races, but fundamentally, races are still part of the programming model that the programs are written in. So I want to back up for this talk and ask the question, do we really have to live with races? And I want to propose an ideal of a programming model in which races just somehow wouldn't arise in the first place. Is that realistic at all? Well, I can point to a number of parallel programming languages that seem to achieve this, right? By kind of redefining the way you write programs. There are pure functional languages. There's deterministic imperative but deterministic message passing languages like Shim. There's languages like deterministic parallel Java that use type systems to enforce separation of parallel activities. And so these are all really interesting approaches. Unfortunately, they mean you have to rewrite all your serial code rather than just kind of parallelize it in an existing language as you might hope to. And so, can we achieve kind of naturally race-free determinism for arbitrary languages? And that's the goal of Determinator. So Determinator is a new experimental operating system that tries to create a naturally race-free parallel programming model pervasively throughout the system API. And because it operates at the OS level, it's compatible with existing languages. And it also avoids races at multiple abstraction levels, like the levels I discussed earlier, shared memory, file system, synchronization, abstractions, and so on. This prototype takes kind of a clean slate design approach, partly for simplicity, partly to avoid to have full freedom of design choices. And I also want to emphasize that the current prototype's focus, although we'd like to generalize it in the future, the current prototype is basically focusing on compute-bound applications. And it's an early prototype with many limitations. You'll see some of them here, and more of them are listed in the paper. But I hope it'll be, illustrative of an interesting idea. So I've talked about kind of the motivation. Next, I'm going to talk about the programming model that Determinator tries to create. Then I'll talk about its implementation and briefly about its evaluation. So a bunch of ideas went into designing Determinator, but kind of I'm just going to describe the one kind of core central idea that kind of pervades the whole design, and that's what I call a check-in, check-out, or working copy model for shared state. And so, in conventional like Linux pthreads, if a parent thread forks a child thread, then the two threads start, accessing the same variables. They're accessing the same memory and interacting kind of at arbitrary points. In Determinator's model, instead, when the parent thread forks the child gets a complete separate working copy of the entire state, and the two threads work in these separate working copies until the next program-defined synchronization point. They never interact until that point, and only at the join point, the system kind of merges the changes the two threads made back together back into the parent. So you might have seen something like this before, probably in a number of in a number of ways. It's certainly not a brand new idea. Very early parallel Fortran systems actually did something like this in their parallel do loops. This was language specific and limited to a particular construct. But obviously, you kind of use this all the time, probably when you're writing software, just at a manual level. Basically, Determinator is just trying to take this concept and see what happens if we try to apply it throughout the system. And so, to give you an idea of how this, might affect ordinary life, when you're developing applications for such a system, I'm going to present two simple examples. They're kind of schematic, but I hope they'll illustrate the key points. So the first is a simple shared memory game or simulator or something where you've got an array of actors representing the state of the virtual world, and at each time step we're going to fork off a bunch of threads. Let's just assume for simplicity that there are only two actors. We're going to fork off a thread for each actor, and that thread is going to go look at the current state of the virtual world, which includes, checking out, reading arbitrary elements in the actors array, deciding what its assigned actor is going to do next, and updating its assigned actor in the array. Well, this is kind of conceptually what we want the code to do. But of course, if you run this code on a standard Linux pthreads, you're not going to get that behavior. Instead, you're going to get something like this. This code is obviously buggy, right? One thread is probably going to get ahead of the others, and it's going to do its reads and start doing its update, and another thread is going to still be in the process of doing its reads to the from the actors array and get partly new, partly old values of the array, and things will get hopelessly confused. So obviously we can fix this by adding more synchronization in standard ways. But let's just take a look at how this behaves in Determinator's model. Basically, in this model, the main thread, running the same code, the main thread forks off these two child threads. But now these child threads get complete separate working copies of in this case, the actors array. And so the threads are reading and updating their actors arrays privately. So they only see the changes they themselves make during the concurrent execution, and only at the join point, Determinator is going to take the changes that each thread made to its assigned element of the actors array, merge all those changes together to form the starting array for the next time step. So that's a shared memory level example. Here's just a kind of again, simple but hopefully illustrative example of what this means in kind of a file system context with process level parallelism. Suppose you have this simple make file that compiles two kind of program-ish things, whatever, and then combines them into a result. If you run this under normal serial make, Make is going to compute the dependencies and then fork a subprocess to compile foo.in to foo.out using this two-stage process. Then it's going to compile bar.in to bar.out. Each of these creates and deletes a temporary file in its process, but it works fine in a sequential setting, and finally it combines these into some output. Now add -j to the command line. Oops, unfortunately this make file has a Heisenbug, right? In this case, it's a pretty obvious Heisenbug. So make is going to fork these two, try to do these two apparently independent compiles in parallel, but because they happen to be using the same temporary file, it's likely that one's going to get the temporary file that was meant for the other or get confused in other ways. But what if you what about if you run the same make -j with this check-in check-out model? So in this case, when make forks the two file systems, they each get separate complete copies of the file system essentially, and of course they're still each of them is reading and writing its temporary file, but only in its local working copy of the file system. And it deletes this temporary file in its local working copy. And by the time we get to the rejoin, where they rejoin the parent, Determinator merges the results of the file system, and now only the foo.out and bar.out actual results are left. It merges those together, and it combines them into the final result. So what happened here? Well, like I alluded to before, there are two types of data races in conventional systems, write-write races and read-write races. Well, the entire class of read-write races just goes away under these semantics because of the way we've constrained how writes can propagate. In particular, writes only propagate via synchronization. So, for example, the read in the thread in the lower left here will only ever see the value of the causally prior write up above, and will never see the value of the concurrent write over by the other thread. So write-write races sometimes go away too. When you get lucky, or when you design your code so that they do. This was the case in the example I just showed, where the two makefile subthreads deleted their potentially conflicting temporary files before they rejoin. But in general, write-write races, if they don't kind of renormalize in that way, they become conflicts. Just like in a decentralized replicated file system. And the difference between a race and a conflict is a race is something that one thread or the other might non-deterministically win, or might deterministically win on a still unpredictable schedule if you run it under a deterministic scheduler, for example. Whereas a conflict is something you always detect at the join or merge point in this case. Determinator just deals with these, treats these as programming errors, just like divide by zero. Although there are other reasonable ways you could treat them too. So I've talked about the basic programming model that Determinator is trying to create. I'll talk now a little bit about how it actually does that. Determinator is a microkernel, and the microkernel supervises a strict hierarchy of process-like entities that we call spaces. And each space is kind of a very restricted analog of a Unix process, in that unlike Unix processes, which can kind of communicate arbitrarily with each other and with the external world, only the root space in a Determinator system can actually directly do any external I/O. And all the other spaces can only communicate with their immediate parents and children. So it's kind of a very restricted communication model. Each of these spaces is purely single-threaded. There's only one set of register state, and it has an address space that cannot be shared with other spaces. So basically, the microkernel is kind of creating the illusion of a shared nothing distributed system full of single core virtual machines. Now, each of these spaces has a private address space, but it also has kind of a second backup address space called a snapshot, and I'll talk about what that's for in a minute. The microkernel API is very simple. It contains only 3 system calls, put, get, and ret, each taking a number of options described in the paper. The kernel does not support any kind of high-level abstractions like processes, threads, files, and stuff like that. Instead, higher-level abstractions are built in the user-level runtime, namely the C library, which currently provides basic Unix-style process management, fork weight, as well as Unix-style and C, standard C file system API. It provides shared memory multithreading both in this kind of naturally deterministic model that I've presented, and also for better backward compatibility. It supports pthreads API via deterministic scheduling in much the same way as you just saw in DOS. So all of these facilities are in a library, so it's customizable and optional, customizable by the application. So just to give you an idea of specifically how Determinator implements its consistency model via these mechanisms, consider a parent thread that wants to fork off a couple child threads. The fork operation is going to translate to a put system call that basically copies the entire contents of the parent space into a particular child space. Not just once, but it's actually going to make 2 copies of the 2 virtual copies of the parent's child space at that point. Once into the main working copy and once into this snapshot position that I mentioned. And then the parent can fork off a second child, or as many as at once. Again, each child gets 2 virtual copies of the entire parent's address space. Now the parent lets them run. They run concurrently. They update their private data. And now at some point the parent's going to want to resynchronize and collect the changes they've made. And so to do that, it's going to make a get system call. And the get system call in this case is going to compare the, in this case, child 1's latest working copy against the earlier saved snapshot that was saved at the fork point. And it basically uses this to do a 3-way diff, and merge between with the snapshot being the reference copy and the child's latest working space and the parent's latest working space, and merge all of those changes back into the parent. And then when the parent resynchronizes with the second child, it does the same thing. And if the programmer has properly avoided conflicts, these changes should go into separate areas of memory, and the parent now has all of the child thread's results collected together. So obviously, all of these copies could be very slow if we didn't do something to optimize them. So obviously, we implement the standard virtual memory copy on write optimizations, and that gets us a long way to getting decent performance, at least for some applications. We also extend standard copy on write optimizations to kind of create a variable granularity opportunistic diff and merge, because it's very common that either only the parent or only the child, or only one thread will be modifying a particular page, and when it detects that, it can just use the appropriate new page and avoid any actual page level work. And so it's only if both threads have concurrently written to the same page that we actually have to do a byte level, in this case, diff and merge. So that's how Determinator supports shared memory. It also, like I mentioned, supports a file system abstraction, at least a file system API. It doesn't support a persistent file system currently. It's more like a scratch file system to provide the familiar process level abstraction that we like. And so it does this by basically keeping a complete copy of the file system in each process's address space. And so all of the processes, since they don't share memory, like I mentioned before, they form a distributed system. And basically, this is a distributed replicated file system with weak consistency. And so when you do a fork, it makes again makes a complete virtual copy of the file system as well as everything else. And wait essentially merges the child's changes to the file system back into the parent's copy of the file system, this time at file rather than byte granularity. The file system detects conflicts at file granularity, and in general these conflicts form what we call hard conflicts, which just produce signal errors. On the other hand, for a particular very restricted class of concurrent writes, we kind of support specially just because, namely, when two processes do append-only writes to the same file, we allow those to happen without actual creating a conflict, because we just merge together the appends, and that way we can deal with log files or console output and things, and we basically get all the appends collected together in a deterministic order. The kernel has some other interesting features. It can enforce this determinism. It has simple distributed computing support via process migration, and it supports this optional deterministic scheduling for better backward compatibility, but I refer you to the paper for that. And so just to briefly give you a brief sketch of some of the evaluation we did. There's more in the paper, but I just hope to persuade you that this programming model can be both efficient and scalable, at least for and enough to be competitive with standard systems, at least for some applications. Certainly not all at this point, for the same reasons as you saw in the last talk. So if we look at some simple compute-oriented benchmarks that we ran, this is on a log-log scale graph, a standard speed-up graph. We see that some benchmarks scale quite well under Determinator, others really don't, especially the highly much more fine-grained LU benchmark. And to compare more directly against the performance of conventional systems, this is comparing absolute execution times, again on a log scale on the vertical axis. This is the performance of Determinator of these benchmarks running under Determinator with respect to the performance of the same benchmark running under Linux for varying number of CPUs, up to 12 CPUs. And as you can see, for kind of the coarse-grained benchmarks, the performance is in the general ballpark of Linux. Sometimes we actually get even better performance, perhaps likely because of different cache effects, or there's many other differences between the operating systems that can account for these kinds of differences. But obviously we get a much bigger serious performance hit for more fine-grained applications. And so, clearly some things this environment isn't, as it stands, isn't suitable for. But to drill down into just one of these benchmarks to kind of get a better picture of how the granularity of parallelism affects performance, you can see that parallel quicksort, for example, just with different array sizes to adjust the granularity with small arrays involving frequent synchronization, we get pretty deep slowdown, but at some point the granularity gets to be sufficient so that performance is again comparable with Linux. So like I mentioned, there are a lot of this is preliminary work, just kind of an early proof of concept. There's lots of ways we'd like to extend and generalize this. But in conclusion, I hope I persuaded you that it is, in theory, in theory seems to be possible to create kind of a naturally but pervasively deterministic parallel programming model that avoids races rather than trying to live with them, and at least for some things it can be reasonably efficient. And thank you, and I'd be happy to take questions. A lot of people lined up, but no questions?
Marcus Aguilera, MSR, Silicon Valley. I was wondering whether your checkout token model resembles more like transactions where you want to provide the isolation property, but you don't care about the other three letters in ACID. Can you comment on the difference?
Yeah, it absolutely resembles transactional memory as well in the isolation it provides. On the other hand, transactional memory systems generally don't try to provide determinism in that just like with the the locking example, locks can be acquired in different orders. Say transactions can run in arbitrary non-deterministic orders in general. So they're not trying to eliminate determinism or races, but they move them to a higher level of abstraction, which is definitely a benefit, but it's a different benefit.
It's ironic that you should mention Marius research and their work in applying. It turns out a concept very much like this in a loop construct which they called pardo, not do all, but pardo. Pardo had the following semantics. Essentially, the environment is copied for every iteration of the loop, and then when the loop terminates, the pages are merged via a three-way diff. The one difference with your work is that instead of trapping, they would just call the result of a write-write conflict undefined. And one could implement that in various ways to get a completely deterministic result. It didn't deal with arbitrary fork-join parallelism, of course. If you're interested in this, it's Computer Architecture News, Volume 16, number 4. Thank you.
Great. Hey, thanks. Yeah, that's very interesting. I'll check it out.
So, based on my understanding, when you fork some thread, those threads really talk to each other. That's what the conditional variable for.
Sorry, I couldn't quite answer the question. Oh yes. So I didn't get a chance to get deeply into kind of so I focused on the memory access model in this talk and not so much on the synchronization level access. So synchronization variables and condition variables and mutexes are a terrible model to program in this, are a terrible fit for Determinator, let's say. They are just not naturally deterministic in their basic semantics. And so in Determinator, we, for this kind of pursuing this naturally deterministic model, we pursued, tried to focus on other types of synchronization, like fork join and barriers. And in theory, we have another associated paper that talks about how you can get kind of non-hierarchical pipeline, for example, pipeline and other non-hierarchical dependency graph synchronization primitives working in a deterministic context. Although that's not, Determinator doesn't support that at the moment because of its kind of somewhat admittedly simplistic, strict hierarchy, strict space hierarchy. So
yeah, but at a very high level, when you fork those threads talk to each other, right? And this model doesn't support those threads talk to each other.
Oh,
they only talk at the end of it.
So they can talk to each other. For example, using barriers, or any other kind of naturally deterministic synchronization. And Determinator already supports that. For example, if you run a parallel subprocess and the process does I/O, it can resynchronize with its parent while it's still running, before it has terminated, and get the I/O and then resume execution again deterministically. I just didn't get into that in detail in the talk. So.
Hi, I'm Eric Eide from the University of Utah. A couple of times in your talk, you talked about how Determinator could support programs written in arbitrary languages. And on the one hand, that's true, but I guess my question is whether or not you think that's really ideal. It seems to me that there are a lot of situations in which you would really like to write programs in a style that knew something about the underlying semantics, right? I mean, if I have threads that are both, modifying shared data structures or extending linked lists or something like that. I mean, anyway, so can you comment a little bit on the trade-offs or the synergy that might be possible?
Yeah, absolutely. So Determinator tries to be completely language agnostic, but having interaction with the languages would be or could be a huge benefit in a number of ways. One detail I glossed over was, how do you choose the right granularity for your diff and merge? And Determinator just kind of arbitrarily choose byte granularity, which means you could get false negatives. You could you might fail to detect conflicts that happen across bytes, among, at word granularity, or you could have false positives if you've got a program that's trying to do shared access to bit fields or, bit vectors or something like that. So it would be better if we actually had kind of language level type system information, so we know exactly the right granularity to merge a particular variable. There might be interesting performance. Obviously you might be able to if you are operating in a type-safe language, you might be able to implement this diff and merge in interesting different ways as well that might achieve better performance, especially for fine-grained applications. So there's definitely tons of potential interesting language.
So do you think that Determinator should support a particular language for doing that, or do you think it should support?
Well, I think it's possible for an OS approach to support language tie-ins without forcing everybody to use only one language. So you can support the desired language while allowing fallback to arbitrary languages for compatibility. So.
Hi, Jason Flynn from Michigan. So the file system portion of your talk reminded me of my experiences using file systems that support optimistic transactions, like Coda and so on. And the pain point in using such systems was in constructing your applications in such a way that they would avoid conflicts or dealing with the write-write conflicts. And I was just curious how much experience you have in figuring out what the programming model is going to be and whether it's going to be easier or harder to write the programs in such a way that they deal with these conflicts.
Yeah, well, so my ability to answer that question in general is very limited at the moment, just because of the kind of, like I said, Determinator is a fairly early prototype. We don't actually have huge numbers of applications and a lot of experience, kind of practical experience. Running software on it, only kind of small parallel shell scripts and parallel examples. On the other hand, we found it, and there are other interesting kind of potential, definitely interesting issues that this model introduces. For example, when an application does a printf, when do you decide to propagate that, to have that child synchronize with its parent and propagate the printf up? Do you try to do those at every program point, or do you batch them up and make them come kind of all together? And that regardless of the choice, you still get a deterministic result, but it can change the user experience. And I don't have a good answer for the exact, I don't know if there is an exact right answer. I'm sure it depends on the application and the context, and so that's an open question.
Okay, we have time for just one more question. Go ahead.
Siddhartha Sen, Princeton University. So the example you showed about the file, the two processes working on the same file, traditionally, I would think of that file as, let's say, processing all its reads and writes in a sequential order, let's say. And it seems like in this new model, the merged file that you produce at the end could produce some kind of order of operations that doesn't correspond to anything sequential originally. So my question is, do I have to change the way I think about my files, or will I have to throw in the usual synchronization to get the kind of behavior I want?
Yeah, good question. So actually, just to reiterate a detail, Determinator currently merges files at file granularity. So if two processes change different parts of the same file, the current version of Determinator won't make any attempt to merge the contents of the files together. It'll only, those will just be a flat-out file-level conflict. But if two processes create two different files in the same directory, then those will get merged together. On the other hand, that said, regardless of what granularity you choose, there's always the potential, the chance that that might not match what the programmer intended. And so maybe the programmer intended, a whole directory to be, kind of one semantic entity, and multiple processes wrote different files that happen to be different, and you get a result. Determinator doesn't flag a conflict, but it's actually a wrong result. You still have potential kind of, false negatives in that sense. And obviously you have.
So I have to be prepared for this, is what you're saying.
Yeah, yeah.
Okay,
or you have to customize the Determinator runtime. So, in this kind of philosophy, you can always dig into the C library, tweak the variables, tweak the granularities, add your, support for your favorite language or something like that. So that's kind of the general approach I perceive as, going forward, but obviously we haven't really gotten down that road very far.
Thank you.
All right, let's thank our speaker.